I recently received this question via email. Hey Henry, a while ago you did a video called What If the Earth Were Hollow, where you showed how long it would take to fall through the Earth. I was simply wondering how that was even calculated since the force of gravity would constantly be changing due to the growing amount of mass above you. Peter. Okay, Peter, so we've got a hole through the Earth, and it goes from the North Pole to the South Pole. That way we don't have to worry about the Coriolis effect from the Earth's spinning. There's also no air in the hole, otherwise you'd reach terminal velocity pretty quickly, and your trip would be slow and boring. There are a few different ways to figure out how long it'll take for you to reach the other side. One is to jump in, but it'll be faster and probably a greater chance of survival if we calculate using math and physics. First, more simplifications. Assume the Earth is perfectly spherical and has the same density everywhere. It turns out that the gravitational attraction from any spherically symmetric object is the same as if all of its mass were concentrated at the center of that object. The closer parts attract more than average, the farther away parts less, but over the whole sphere, it averages out. In a similar vein, if you're inside a spherical shell, then the gravitational pulls from all the different parts cancel out and you experience zero effect from the shell. This means that inside the Earth, any parts that are farther away from the center than you are cancel out and have no effect. Almost like they've been trimmed off and you're temporarily on the surface of a smaller, shaved Earth. Since we assumed the same density everywhere, the shaved Earth's mass is simply proportional to its volume, which is proportional to its radius cubed. And because it's a sphere, we get to pretend all that mass is actually concentrated at a single point in the middle. So how much does the shaved Earth point pull on you? Well, the gravitational attraction between two objects is proportional to their masses, but inversely proportional to the distance between them, squared. So we have to divide the mass of the shaved Earth by the square of the distance you are from the center, which is just the radius of the shaved Earth. R cubed divided by r squared is r. So the force on you is simply F equals some constant stuff times r, your distance from the center. Essentially, as you fall, the mass beneath you decreases, while the average gravitational pull on you from any bit of that mass increases, but the mass decreases more than the average pull of gravity increases. So as you approach the Earth's center, you go faster and faster, but the force pulling you towards the middle gets smaller and smaller. Exactly in the middle, you experience zero net force, because the Earth is pulling you equally in all directions. Though since you're going so fast, you'll continue to speed on towards the other side, gradually slowed by the now increasing force pulling you back towards the middle. The exact same equation, some constant stuff times a distance, also describes a mass on a spring, or a simple pendulum, or a cat in a parabola. And from studying those equations, we know that the time taken by the moving object, whatever it is, to go from one side to the other has a simple formula. Pi times the square root of the mass divided by the constant stuff. In the case of falling through the Earth, your mass cancels out of the equation, so we just need to put in numbers for the density of the Earth and the gravitational constant to get the answer: 42 minutes to fall through the Earth. This turns out to be exactly the same as the time it takes to fall around the Earth to the other side, and it's the number you'll find commonly mentioned on the internet. Even more surprising, the radius of the Earth didn't factor into the time calculation. It predicts you'll take 42 minutes to fall through or orbit around to the other side of any sphere with the same density as the Earth. But the Earth isn't exactly the same density throughout. We know from seismology that the Earth's core is much denser than its mantle and crust. So as you begin to fall, most of the mass is still below you, pulling. So the pull of gravity doesn't decrease as much as our simple model predicted. In fact, the force is actually pretty constant until about halfway to the center, at which point it starts quickly decreasing as more and more of the Earth is above you. The calculations here are a bit more annoying because we have to piece together two different parts: the falling with constant acceleration part, which is easy, and the falling with decreasing gravity proportional to your radius part, which is the same thing we did before, except now you're starting out halfway to the middle of the Earth with a speed of 17,000 miles per hour, instead of on the surface with no speed. Once our mathematical dust settles, we combine the two parts and multiply by 2 to get the total travel time to the surface on the other side: 37 minutes. Of course, this is still just an approximation, slightly more realistic than before, but far from perfect. If you carefully piece together the time for a falling through the Earth trip based on a more detailed density profile of the Earth, like maybe the preliminary reference Earth model, you can be even more precise: 38 minutes and 6 seconds from pole to pole. But either way, if instead of calculating you jumped into the hole at the start of this video, you still have a long ways to go before reaching the other side of the Earth. Safe travels! I'd like to thank Audible.com for supporting this video. Audible is a leading provider of audiobooks including fiction, nonfiction, and periodicals. For example, they have Nudge by Richard Thaler and Cass Sunstein, a book I read several years ago that opened my mind to some of the hidden reasons why we do or don't succeed in making changes in our lives, and which has influenced my thinking ever since. You can check out Nudge or another book of your choice for free with a free 30-day trial at audible.com/minutephysics. Again, that's audible.com/minutephysics.